Hey. Ý ra ngoài có cái gì để trên trên này aquele deixando lá, fazendo assim.
Então, boa tarde a todos, obrigada pela presença. Olá aos que nos acompanham pelo YouTube. Então, dando continuidade ao ciclo de seminários, né? Essa apresentação de hoje faz parte do ciclo de seminários do Departamento de Estatística da UFRN. Na palestra de hoje, nós teremos novamente o professor Geoff, do Departamento de Estatística da Virginia Tech. Ele vai nos apresentar uma série de 3 seminários. E nesses 3 seminários, ele vai falar sobre a regressão Weibull aplicada à confiabilidade. So, it's nice to receive you again, Professor, and thank you for availability. Thank you. Good presentation.
Boa tarde. That's as close as I'm going to come to Portuguese. Just a few words. Obrigado is my favorite one. The idea is I'm going to do a sequence of 3 lectures, and today is the introduction to it. The ultimate goal is for me to show you some of the stuff I'm doing in NASA, lecture 3. But we've got to lay foundations first. And let me convey the complexity. Historically, reliability analysis has been in the domain of the mathematical statisticians. They think in terms of mathematical statistics. Modeling is much closer to regression analysis. The people who understand mathematical statistics rarely know very much more than introductory regression analysis. And the people who really know regression analysis know nothing about reliability. Now, full context of this, I've been on this project for 13 years, and we should have finished 2 years ago. But proper analysis of the data, which is Weibull regression, demonstrates that the theory, all the theories this particular community has, are wrong. Let us just say that's controversial. So far, so good? The engineer, who is the subject matter expert, planned the perfect experiment to test every one of his theories. And they are all wrong. Are we interested now? When we get to lecture 3, we'll talk about some of those issues. Fair enough? But the intent today is to start with basics. We'll go one step further next week, and then that'll be enough material for me to introduce kind of what the situation is. It's been very interesting, very interesting. So I have learned a great deal from this, and I hope you will appreciate it. But it's a unique opportunity. I'm a regression person who's learned reliability. So I can bridge the gap between the 2 worlds. I want you, over the course of these 3 lectures, to see them. Fair enough? Feel free to ask questions anytime. Are we okay? So, let's go to the first slide. Okay, so this is the outline for this. I went back to one of the very first papers by Weibull. Now, actually, his name is not Weibull. He's a Swede. It's Weibull. But only in Sweden do they say Weibull. Everybody else in the world calls it Weibull. Okay? I got to speak at the University of Stockholm under a picture of Weibull. They're very proud of that. And I never paid much attention to the details about the derivation of his distribution. But for this lecture, I really went through it, and it was fun. And part of it is engineering. A lot of his intuitions are engineering, but ultimately it has an engineering interpretation, but it's ultimately purely empirical. Fair enough? That is a very important conversation as we go along dealing with my NASA team. The engineers think of this as science, okay? But I want us to appreciate ultimately it's an empirical model, but it has an engineering interpretation. We are going to play only with the basic 2-parameter Weibull distribution today. That's of minor interest to me. But the next lecture, we'll go to the analog to simple linear regression. And then in the third lecture, I'm going to deal with much more complicated models. So far, so good? So I want us to build our understanding. One of the unique things about reliability in the Weibull distribution is the hazard function. And I want us to understand the hazard function because in the last few months, I have discovered that is crucial for me to make my arguments to the NASA review board about what's going on with the project that we've been playing with for 13 years. But the hazard function is an instantaneous risk of failure. And that's really very insightful. And that's something that regression people have no analog, but it's fundamental to engineering reliability. Okay? I'm going to talk briefly about the foundations of estimation and inference. It's all maximum likelihood, all likelihood statistics. But let me give you a hint. Regression analysis is focused on residuals. So far, so good? Maximum likelihood is focused on residuals. Most of us don't realize it. So far, so good? And I'm going to illustrate that in infinite detail. I think that's a crucial insight for what's going on here. It leads to some of the misunderstandings between the reliability community and the modeling community. But ultimately, they're always going back to residuals. I want us to see it. Censoring is essential to reliability tests. They take a very long time to get things to fail. One of the things we're going to be interested in is extrapolating to a use condition. Extrapolation is always dangerous. So far, so good. But that's going to require the building of at least a simple linear regression model to allow us to do that. Right censoring is a vital component to all of these tests. In my NASA experiment, out of 708 test items, only 48 were exact failures. That's 660 right censored observations. Have I got your attention? Heavily censored. How do we deal with censoring? Biostatistics deals with this issue, but in my life as an engineer, it's in reliability. I'm going to talk briefly about Weibull probability plots to set the stage for the next lecture, where in regression analysis, you go into any of the standard software, I like Minitab, okay? How many different kinds of residual plots can you get? You've got a normal probability plot. Probably, the residuals by predicted value, residuals by time order, residuals by the regressors. None of that exists in the reliability world. None. They're insightful. They help us understand. Welcome to lecture 2. Okay? But I need to set the foundations today. And in order to come up with the right residuals for plotting, we have to learn how to standardize them. So I'm going to start that conversation today, take it to another level next time, and then we're going to really look at some plots. So far, so good? And I have an example, and it's the only one where I can give you the data. I'm going to summarize the others. If I can come up with a homework case where I can give you data, I will. But the data are now considered by NASA as sensitive but unclassified. That's just below secret. Okay? I cannot even tell you the material that it is, much less the parameter estimates. I would love to show you the parameter estimates. I would love to show you the full analyses that I get out of Minitab for what I do. I cannot do that today. We expect to be able to publish this in the open literature, but we have to get NASA approval first. So far, so good. Okay, so I wish I could show it. But we'll be introducing some we'll introduce the basic Weibull plot. We'll do more next time. Are we seeing where we're going? Are we okay? Next slide, please. The paper that I used to provide some foundation for this is basically a talk that Weibull gave in 1951 at the American Society of Mechanical Engineers. It appears in one of their publications. So he starts off, this is literally how he does this. He starts off with any CDF can be expressed as 1 minus that crazy function there. And that crazy function is nothing more than a survivor function. Now, I know that when I was taught statistics, there was the PDF and the CDF. And that's all we ever talked about. So far, so good? Well, the survivor function is really important in reliability. And notice what it's defined as. S is that survivor function. It's just 1 minus. If the CDF is the probability it fails up to this particular time, the survivor function is the probability it lives beyond that time. No rocket science. Are we good? Okay? But reliability, people, it's the survivor function that's of primary importance, not the CDF. Okay? What's the likelihood it survives? For example, they measure in aerospace and military applications the probability of survival in terms of the number of nines. 1 9 is the probability of survival is 0.9. 2 nines is 0.99. The norm in NASA for a component is 6 nines. That the probability of failure at the use condition over the mission life, expected mission life, is 0.99. Probability it survives is 0.99. 9999. Okay? Now, there's a joke within NASA. One time, Wernher von Braun was brought into the NASA director's office, and this was dealing with one of the early programs. Success was vital. And NASA was saying, okay, now, are you sure that this particular system has 6 nines of reliability? And von Braun apparently said, of course it does. And he brought in 6 of his engineers, and he asked each one of them, what's the probability it will fail? 9. What's the probability it fails? 9. What's 9 in German? It's not going to fail. That's how he got his 6 nines. Oh, sorry, magic. However, the key here is that Weibull is saying that it's of that form, but you know, that's trivial. You know, all you do is take whatever it is, take the log, you know, that doesn't say anything. So far, so good? Okay? Next slide. Now then, he says, let's consider that I'm dealing with a system. So failure is going to be as a result of some component in the system failing. So I'm going to say they're independent components. And we're going to assume that the system fails and any one of these components fails. That's the assumption he's making. So survival then means that all of the components still have to be functioning at whatever time we're looking at. Does that make sense to people? Okay? So far, so good? Now, there is real engineering insight into this. Okay? Next slide. So I'm going to let S sub S be the survivor function for the system, SCU being the survivor function for critical components, U just being an index. And what we do is, if we can assume that we can just multiply them together. Okay? So far, so good? That's what he does. What Weibull is assuming is a very important engineering intuition. Failure is due to the failure of the weakest link. So far, so good? When I first started working with reliability, I was working with Pratt and Whitney, and they were very much into Weibull. Abernathy wrote the Weibull handbook when he was at Pratt and Whitney. It's a Bible for many people in aerospace for how to deal with reliability issues. And Abernathy, was just over the top about Weibull. And they made made a big statement, a lot of conversation around, this is the engineering basis for the Weibull distribution. It's failure of the weakest link. So far, so good? That's how the engineers are viewing this. Now notice in this form, though, this isn't going to the actual form of the Weibull distribution, but this is the notion of failure due to the weakest link. Are you getting my drift on this? Is there an engineering intuition to what Weibull is doing? Yes, but when we get to the final form of it, it is empirical. So far, so good? This leads to interesting conversations with engineers. Okay. Next slide, please. He assumes he has no idea what is the weakest link, so he says he's going to treat each as equally likely, and he's going to assume independence. So far, so good? If that's the case, then the survivor function for the overall thing is this thing right here. He makes a lot of noise about that. He says this is an incredible insight, and that's fine. But then he also notes he has incredible flexibility in choosing that function. So far, so good? It's still failure of the weakest link. But how are we modeling the probability of failure for a specific component? I don't know. Okay? See my point? Next slide. He says, let's use this thing right here. Okay? So this is out of the blue. This is what I want to use. And generally, when you see a Weibull distribution in a textbook, they don't have this constant, this parameter T0. But he does this in this paper, and it's important for him as he tries to apply his distribution to other situations than reliability. In reliability, the time to failure has to be positive. Okay? It has to be greater than 0. 0 is the natural bound for that T0. But what he says for it is the limit of S of T, and the limit of the survivability of the function of the system, as T decreases to T0, has to go to 1. You got the idea here? T0 is the absolute earliest anything could fail. For Weibull, it could be negative, by the way. But in the reliability applications, we're always looking at things like loads, which have to be positive. We're always looking at times. We're looking at voltages. We're looking at characteristics like that. So generally, in the reliability applications, it's 0. Beta is called the Weibull shape parameter. Now this gets confusing because it will be called a scale parameter when we talk about the smallest extreme value distribution. Eta is usually called the Weibull scale parameter. You see what I mean by being confused about what we mean by scale, okay? But beta is the Weibull shape parameter. Eta is the Weibull scale parameter. We'll call it the characteristic life because I'm dealing with times, but it could be the characteristic load if I'm looking at strength. It's just whatever the characteristic is. There is no basic engineering justification for this one. None. 0. Okay? Just common sense. Fair enough? Nothing magic. Keep in mind, for a lot of engineers who are dealing with this, who have very little training in probability and statistics, this is the gospel truth. This is the model that you do to predict the reliability of your components. They will call it science. We need to recognize it's empirical. Fair enough? Okay. Next slide. Here's an explanation of the scale parameter. I changed the order than what I had in the reading material. So this line right here is a, remember right, it's a beta of 0.1. So this is extreme, look, it starts out with extreme probability, likelihood of failing early, and then it tails off. So far, so good? That's going to be important to us. Here is the exponential distribution. If you pick up the statistics literature on reliability, the dominant distribution in that literature is exponential. If you look at an engineering reliability expert and talk about the exponential distribution, they will look at you like you're an idiot. Did you just get my picture here? I want us to understand why. So far, so good? So a lot of the statistics literature is really focused on the exponential distribution, and there's some reasons why. But when you talk about an exponential or a gamma distribution to a reliability engineer, you might as well walk out of the room because you no longer have much credibility. I want us to understand why, and that's going to happen in a few minutes. So far, so good? Okay. Beta equal to 3 is almost a normal distribution. Okay? Very cool in that regard. Beta of 5, this was done by a PhD student of mine for illustration purposes. That's this one over here. This was beta equal to 3. She described that as extreme wear out. I'm going to show you with the example that we have today, a beta of 27. Is that a whole lot bigger than 5? That's what I would call real rapid wear out. So far, so good? So we're beginning to describe what's the likelihood of failure, and that's important to our instance. Next slide. It's a member of the smallest extreme value distribution, and that's actually very valuable to us as statisticians. This is where we can see the link to ordinary least squares regression. This is where we can see that it's actually a residual that drives everything in terms of the log likelihood. And as a result, that's essential, that's the key to the analysis. But that also then says that's the key for how we can do proper residual plots to get additional insights. It also indicates that we can simplify the process for taking derivatives, which are essential. Because everything is going to be asymptotic in terms of the inference. The information matrix is extremely important, which is the matrix, the negative of the matrix of second derivatives. So I want us to be aware of that. So just playing with the math, I can re-express the survivor function in this form right here. And notice I have an ln(t) minus an ln eta. Eta was that characteristic strength, okay, or characteristic life. Well, we're going to call that mu. So for the SEV, the location parameter is called mu. So mu is going to be the log of that eta. Oh my, this is ln(t) minus mu. I'm going to call the scale parameter, the SEV scale parameter, sigma, but it's going to be related to beta. It's just the inverse of beta. Oh my, oh my. Doesn't that look like a standard normal kind of thing? Random variable minus its mean divided by its variance, its standard deviation. This is not a standard deviation, by the way, but it has a similar connotation. It's a true scale parameter. The smallest extreme value distribution is a member of the log location scale family. Okay? At some point in lecture 2, I will call this Z with the natural inclination to take it back to normal theory. At that point, I'm using notation from Meeker and Escobar because they call this thing, this standardized thing, Z throughout their book. Okay? But it's centered and scaled in an appropriate fashion. It's a scaled residual. Okay? Ordinary least squares. You know, sums of squares residual. What are we doing? We're trying to minimize the sum of the squared residual values. Hello. Doesn't that drive all the inference? Are we getting the picture on this? This is the point where we can tie together ordinary least squares kind of approaches to reliability. The key is for a Weibull distribution, the random variable would be t. For the SEV, it's log t. We can use one or the other. It's just like we could be dealing with normally distributed data, or we could center and scale it and play with the standard normal distribution. The analyses will be equivalent if we do it correctly. Are we okay? So far, so good? Next slide, please. Here are the density functions. Now, when I deal with the engineer, he will deal with the function in either this form or this form. So far, so good? So he likes playing with the probability density function. When I was taking math stat in grad school, how do we do maximum likelihood? We always went to the probability density function. That's a mess to play with. Have I got your attention? Once I start expressing this in terms of the residuals, log likelihood is trivial. So far, so good? Pain. Pain, but if I re-express this in a different way, and I start taking logs, not so painful. And in fact, I can write a very simple expression that would cover every possible Weibull regression problem. Because I'll express it in terms of the scaled residuals. Are we okay? Now that involves taking derivatives relative to the scaled residual, but that's a very trivial thing to do. Okay? But conceptually, it's a very nice framework. This is the hazard function. How many of you have ever seen a hazard function before? Oh, good. 3 people. That's great. More than I expected. Okay? Now, this is something I always thought was, okay, why do I ever want to play with this? I discovered about 4 months ago, it's almost essential for me to explain to practicing NASA engineers a very important issue in our proving that the theory is wrong. Okay? So what it is the probability density function divided by the survivor function, and the interpretation of it is instantaneous risk of failure. Okay? So far, so good? Then you say, that's great, Geoff, who cares? We will care here very soon. We will really care when we get to lecture 3. Fair enough? Okay. Next slide, please. I told you earlier that statisticians love the exponential distribution because if they can standardize the Weibull, they can map any Weibull to an exponential. Problem is they're making an assumption that's not telling. Okay? That's an issue, but everybody likes to make things simple. Statisticians oversimplify. Okay? It explains how the risk of failure changes over time. So for an exponential distribution, beta equals to 1. So far, so good? Okay? Let's go back to the previous slide. Beta equal to 1. 1 minus 1 is 0. That's gone. That's constant. No function of time. As far as reliability engineer is concerned, that's worthless. That's an example of things are failing at random and there are no failure mechanisms associated with it. We don't know what they are. That's a problem. I call that just random failure. I got your attention. Okay? So let's go back to the other slide, please. That's what I mean by it's 1 over eta. The exponential distribution is random failures. And they'll just look at you and stare at you like, why are you wasting my time if you're talking about an exponential distribution? There's nothing interesting about that. Okay? Next slide, please. Many people have heard of the bathtub curve. Now, there is no way that you can model a bathtub curve with a single Weibull distribution. However, you can do incredible things by breaking that curve into sections and recognizing early in the process you have one failure mechanism, Suddenly you get past that failure mechanism. It looks like random failure. Hello. And then you finally get to what will be the final mechanism, which is wear out. So far, so good? We plot those hazard functions. You will see something that looks like a bathtub. Okay? But before I get there, infant mortality is when we have a lot of early failures, and once you get past that, you don't see failure for a while. My NASA experiment goes back to, they took 57 cords of fiber. I can't tell you the material. Put a dead weight on for 10 years. 57 of them, 10 years. And what did they learn? They either fail immediately or they last forever. I have seen vessel tests at White Sands, okay? 10 years, very high stress. They either popped very quickly or they're still there after 10 years. Classic infant mortality, okay? You see this with semiconductor parts. You know, the initial load, it's either going to fry it and you get rid of the bad ones and then it'll last for a very long period of time. Infant mortality is associated with a beta of less than 1. Beta is very important in terms of interpreting reliability results. Random failure, beta is approximately 1, exponential distribution, nobody cares. When we get to wear out, beta gets larger than 1, and in some cases, very much larger than 1. We'll see some fun things in lecture 3. We okay? Here's a bathtub curve. This is based on, but not exactly my NASA data, because we can't see out here. We cannot see out here. If I remember right, this is real NASA data for a hazard function. But in order for me to illustrate the bathtub curve, I had to make something up out there. Are we okay? If we're at the use condition, the real wear out mode is probably measured in centuries, if not millennia. Notice, very steep. This is a beta very, very near 0. So high instantaneous risk of failure, and then it stabilizes out, and it looks like there's almost no chance of failure for a very long period of time. The beta is very near 1. To the eye, you wouldn't be able to see it. It is so close to 0, and it looks flat. We will see some of these plots in lecture 3. And it really is kind of a smooth junction here when we get to those data. And then you eventually run into what would be the mechanism that causes failure. So that's the rapid wear out. I will show you examples of rapid wear out. I will show you examples of infant mortality. I will show you examples of random failure in lecture 3. Okay? Are we getting the picture on this? For the reliability engineer, this is an extremely important plot. When we're dealing with the reliability engineers, the less we talk about p-values, the less we talk about how we estimated it, the more we show pictures that clearly convey what the data are saying, the more likely we are to be persuasive. Something that took a long time for me to really appreciate. Okay? Next slide, please. The fundamental bases are going to be maximum likelihood, log likelihood. We're going to be doing all of that. I'm not going to emphasize a lot of the details, although I will show some. The Hessian, which is the inverse of the information matrix, is important for Newton-Raphson. So all of the Weibull estimation involves iterative solutions, numerical solutions, but it's also important for the variance-covariance structure. A lot of software goes to more non-parametric approaches to the iterative solution, which is fine, as long as it does converge to the correct Hessian, because ultimately the variance-covariance structure is important to us. But the key to understanding log likelihood, and that's what I want to spend some time on, is seeing that it's really being expressed in terms of these things. I want us to appreciate it. So for the first part of this, I'm going to consider only exact failures because life gets to be more complicated when we have sensors. Not much more complicated, but it's not intuitive. Are we okay? Next slide, please. Here is the likelihood function. This is based off the PDF for a single observation, single time. So all that is, I take a log of it. By the way, I had a typo in the reading material, so I didn't look at it carefully. So if you take the log, then suddenly you get this crazy looking thing here. If you rearrange it, this is a beta minus 1, but I can rearrange it and get it into this form. It's an LNTI minus mu. It's a residual. So far, so good? It's a residual. So what do you think I'm going to do in the next slide? I'm going to replace that thing, which is cumbersome, with something that's very simple, residual term. I can generalize that any way I want to. The only thing that will become more complicated is the mu function. We'll see that next time. So far, so good? Next slide, please. Okay, so I define that to be the residual. This looks more like the residual if the random variable is log time minus its mean. It's not its mean, but it's the location parameter for that particular characteristic. I like to talk about the scaled residual. In regression analysis, I really emphasize, I don't hold a co-author of a book. We don't deal with raw residuals. E sub I is an example of a raw residual. I don't know if that's big or small. But proper residual plots in regression should always be scaled in a way that we can interpret them. The externally studentized residual is my preference because I know it follows a t distribution. I can evaluate size. Asymptotically, beta times E sub I will follow a standard normal distribution. Asymptotically. I always get worried about that. How big does the sample size have to be in order for the asymptotics to kick in? Remember, out of 708 test items, 660 were right censored. Only had 48 exact. That's not a lot of information. Am I conveying the issue here? So I get a little concerned about asymptotics. At what point do they kick in? This is important for understanding the next two lectures. U is always just going to represent the deterministic part of the model. Right now it's very simple. The interpretation is the equivalent of a mean. But I can come up with more complex functions. Beta represents the spread, and I'm going to use the term spread, not variance, because the variance for the Weibull depends on the other parameter. You never hear reliability engineers talk about variance. Never. It's irrelevant. Okay? What are they interested in is the beta, and it's the spread given a specific value for the deterministic part. That's what they're interested in. Okay? But I think this is fundamental. You talk to a reliability engineer about the variance, they're going to look at you like, why? Well, we're statisticians. We always want to standardize by our variables by standard deviation. And if I want a standard deviation, I got to have a variance. They're not scaling by a variance. They're not scaling by a standard deviation. Are we getting the picture on this? They've already got a scaled variable that asymptotically follows a standard normal distribution. Why do they need a standard deviation? Why do they need a variance? They don't. Why make life complicated? Why force them into our world when it's irrelevant to what they're doing? Are we understanding communication issues? Right. Next slide, please. Right censoring, sitting there and putting a dead weight, even if it's a really heavy weight, that thing is either going to fail immediately or last forever. That's not unusual about a reliability test. You're looking at lifetimes. Ideally, it should have a long life. It's hard to see that. Okay? Next lecture, I'm going to talk about accelerated life tests, where I'm going to speed it up. Okay? But right now, we're just talking about, I'm going to put it at the use condition and see if it fails. Okay? So far, so good? Sooner or later, you got to decide, okay, do I have enough information where I can make a decision? So that leads to the notion of right censoring. So as the time moves further and further to the right, we make a decision, is this time to stop the test? Now, do we have complete information about that failure? No. But is there some information? Yes. So far, so good? I know it lasted at least this long. When we look at accelerated life test, it used to be NASA would throw away any level where everything was right censored. That's dumb. Because you may have had 20 items survive that. And there's information there. It at least survived that long. We don't know when it would have failed, but it at least lasted that long. There's not no information. There's limited information. Right censoring helps. By the way, you can estimate a Weibull distribution, 2-parameter Weibull distribution, with one exact failure if you have at least one right censored observation. Did you hear me? One exact failure and at least one right censored, you can estimate the parameters. That's counterintuitive. B.J. Nair, when he heard that, said, "You got to be kidding me." No. It's an exercise in Meeker and Escobar. It's cool to be able to show that. Because Pratt & Whitney, if there was a new jet turbine, new family of turbines put on Navy aircraft, the Secretary of Navy was calling people at Pratt & Whitney the moment there was that first failure. So they had to be able to respond to it. The estimate is horrible, but it can be done. I want us to appreciate the reliability world is a little different. And the proper basis for the likelihood is not the probability density function. We don't have that, but the survivor function. So that's what we will be using to construct the likelihood function. Next slide. So I'm assuming inexact failures are right censored. I'm going to let T sub C be that censoring time. So EC is just the residual relative to that time. Just for convenience, I'm assuming they're all being censored at exactly the same time. Okay? Doesn't have to be. Makes this expression simpler. So the likelihood for all the test items, here is the likelihood contribution for the exact failures, and here is the likelihood function. There are R of them, so I've been multiplied by R. We're assuming that we had a completely randomized design. Okay? And that's very straightforward. This will be exactly the same likelihood function that will be used for more complicated models, because I have expressed it in terms of the residual. Okay? Now, how do we find likelihood, the maximum likelihood estimates? We would take the derivatives of these things. That's fine. The derivatives of the residuals usually are very trivial. Makes this a whole lot easier operation. Okay? Well, trust me, I had to do all the derivatives. God created graduate students for multiple reasons, programming and finding derivatives. Well, I don't have a grad student working on this NASA project. And my junior colleague was caught up doing programming for the other engineer. So I had to do all the derivatives. Oh God, it was painful. When I saw how I could do it this way, it made my life much easier, right? And everybody on the team has said, except for the engineer, said, thank God I went through and did the derivatives, because I learned a lot. Okay? Oh, but it was painful. I hated it when I was young, new. I'm old. But it's not bad. We're getting the idea here. So far, so good? Okay, next slide. Weibull probability plot. I talk a lot about it in the reading material. I'm going to summarize it here. I talk at least as much about it in the next lecture. Now, I will probably not go through all of that in the slides, but I want us to appreciate how we can standardize. So I'm expecting the first pass, as you see how we do the residual plots, going, okay, I have an idea, but I really want us to appreciate how we can come up with the proper analogs to ordinary least squares next time. Okay? They're important plots. We go through, I show the derivation of this. This is, that plot should lead to a nice straight line if the data follow a Weibull distribution. Are we okay? If you're really interested in the details, it's like a 4-line derivation. It's not rocket science. But that would be the straight line in terms of this. Ultimately, all of our residual plots should be viewed in terms of this scaled residual. I want us to get our instincts there. I'm going to give you an example where I'm going to show the Weibull probability plot in terms of the actual characteristic of interest and in the scaled residual. And you'll see they're exactly the same. Okay? Scale changes. Are we good so far? Okay? Next slide. These are real data, actual data. Okay? These are the data for my test. This is the tensile strength test. You're getting absolutely no information beyond what was the typical strength of the cord that we used. And I can't even tell you what the cord is. So there's absolutely nothing useful here. So far, so good? Okay. I've given you the data. I have not given you the mini-tab analysis. You can use whatever you want to, but have fun. Write it up in R. I have R code only. The R code requires an iterative optimization function. And as I said, God created graduate students for a reason. I don't want to learn how to implement the proper optimization functions in R. I'd rather leave that to my colleagues. Okay? I've got Minitab. It works just fine. Now, when we come to lecture 3, I can no longer use Minitab. And there will reach a point where I can't use it. But at that point, I have my NASA engineer who programs everything and my colleague well trained on what to do. So I'm fully confident in it. Oh, and by the way, I'm never fully confident in graduate students until they prove it to me. And that's a classic whenever we go out and do something new. I want to make sure that they check it, they write it in R and check it against stats. Okay? I don't necessarily believe R, but if they can get the R to look like SAS, I'm beginning to feel comfortable that both may be right. Fair enough? Okay. I used to be able to code, but I'm too old now. So I've given you the code for the probability plots because I think that's a cool thing that you're not going to see in other software. It's easy to get the optimization routines. Okay? So next slide. There were 77 items that we did in the tensile test, and it's unusual, but we actually had right-censored observations. The original test at Lawrence Livermore Lab from 1995 to 2005 had metal clamps for carbon fiber. What does metal do with fiber? Cuts it. And if you cut part of the outer layer of a cord, are you increasing or decreasing its strength? It's a bad thing. So the engineer planned to use epoxy so we wouldn't cut the outside layer of the cord. That's a bright idea. Okay? He never bothered to test if it would really work. Hello. Why do I bring that up? There are 14 right-censored observations. Tensile strength test is it's on a vertical system and you just pull it. You start applying a load. So it doesn't stretch much, it's going to stretch a little, but you just start applying that load to it. Some of them began to pull out. He hadn't tested whether the epoxy would really work. So far, so good? We got it fixed. The strength tests were done over the entire period of the study. So we were making sure that the tensile strength didn't change. This was a 1-year-long experiment. Long time. So far, so good? But these 14 right-censored values are where it slipped out, and all we knew is it had at least that much tensile strength, but we didn't know where it would have really failed. Classic example of right censoring. This is one of the few tensile strength tests where you would ever see right sensor, but allowed me to show you some really cool data. Fair enough? These are the real data. This is the typical mini tab, the sensor value, you got to specify all that garbage. Notice it's load, so the measurement is in pounds force, not kilograms force, but we did it in pounds force. Okay? Next slide. Here are the parameter estimates, and you know, this is a 2-parameter Weibull, and those are the parameter estimates. You know, you might want to say, well, should I test whether or not the scale is 0? Who cares? The scale's got to be greater than 0. We got to make some points here. But this leads the engineer to do some strange things once we get to more complicated models. Okay? That's the model. The only issue is, should we use a Weibull distribution or should we go with some other distribution? But they're going to be 2 parameters, okay? Unless it's more complicated. So the formal tests don't make any sense. Looking at the confidence interval, that's just giving us some sense of how precise our estimates are, but there is no need to do testing at this point. You're stuck, okay? The log of likelihood is going to become important to us starting next lecture, because I'm going to talk about mother models, okay? I want to evaluate the equivalent of simple linear regression, but I want to compare it against what would have the absolute best possible log likelihood. So far, so good? It's a classic way of doing testing with log likelihood statistics. I need that full model. And this is where the engineer has no intuition, none whatsoever. It's not his world. We'll see that next slide. Next slide. There's the normal plot, the Weibull plot from Minitab. I really dislike Minitab doing 2 standard errors. And by the way, there's a lot of approximation on this, and you see it in the reading material. And I'll talk a little bit more about it next time. I'll talk more about the generation of this, but you're exposed to it in the Lecture 1 reading material. But 95% confidence band, when you're dealing with a large number of observations, if people get really upset when you see a point outside of those bands, I have a problem with that. And particularly since we're dealing with asymptotics, and we're dealing with a lot of other issues, okay? People can get bent out of shape. But that's not a bad-looking plot. Now we have this baby out here. So far, so good. Minitab will not allow you to change it from 2 standard errors. I wrote R code. I can do it whatever I want. See why I did the R code. Also, I do the R code, we'll see next time, I'm colorblind, okay? But color coding is important. I don't see green light. 5% of males are my form of colorblind. So when people do cool color presentations, it may be cool for me or it could be garbage. So if I'm going to do plots with color, I want to make sure I can see it and people like me, okay? 5% of males. So that's the reason why you will be getting R code for probability plots, because I want to show them in specific ways. Okay. Does the assumption of a Weibull distribution look reasonable to all of you? That's about as good as you're going to get on some of these reliability plots. Okay? So far, so good? Now notice this is in terms of the load. Okay, this is the default Weibull plot out of Minitab if you just fit the 2 parameters. When we go to the analogs of simple linear regression and more complicated, everything is going to be scaled residual. Okay? So the next question is, why don't we look at the scaled residual? Are we okay with that? Okay, so let's go to the next slide. Here's the Minitab analysis on the scaled residuals. Theta times log t minus the mu, log n, log a. It tells us this smallest extreme value. So far, so good? Okay. And let's go to the next one. In theory, if this is really all going perfectly correct, if I've really standardized it correctly, we're going to see some issues with that. This should be like a standard normal distribution. So the location parameter should be 0. That's arbitrarily close. and the scale should be 1. This is nice. Now we start constructing compound scaled residuals, life gets more interesting. And we will talk a little bit about that in lecture 3, okay? So I just want you to be aware. But in the simplest case, then it's going to be, the location should be 0, the scale should be 1. This law of likelihood is going to become important to us, and I'll talk about that next time. Once again, looking at formal tests is not really useful, but seeing if it's 0 and 1 is. Next one is just the plot. So let's look at that. Looks the same. Oh, let's go to the next one. We go to the next one, we see it side by side. Are they the same? They should be, because the plot for load is really based off of the scaled residual. Am I making my point? When we generalize, we're not going to be looking at the original characteristic. It's only in the simplest case we do that. For all the other cases, we're going to be in the scaled residual. I want us to be comfortable there. So far, so good? I'm throwing this into the regression world. This is all math stat, but I'm adapting it so that it is very comfortable for somebody who's done a lot of analysis from regression. Because that's ultimately all that we're doing. We're just changing the distribution. Okay. And I think there's 2 more slides. Here's that plot that I generated, and it's basically the same, but you see that the confidence limits are a little wider. Are we okay? By my preference. I'm going to have a tendency where I really am interested in groups to have it color-coded. So next time we're going to have 3 groups. We're going to have 3 different stress levels, and we're going to do an accelerated test. And it's important to be able to see what's happening as we change the stress levels. Intuitions are very different than ordinary least squares. And I want us to appreciate that. Are we okay? So far, so good? The intent of today was just to get us started. Now, I don't know how many people have ever played with the Weibull distribution, but this is just a quick introduction to it. And that's the reason for the reading material. So, if you're really interested and you didn't quite catch some things, go back and look at it. If you want to talk to me this week, that would be great. But the more we understand this lecture, the easier it will be to extend it to simple linear regression, which is not a big extension. Lecture 3 is going to be, we're going to the frontiers, okay? So far, so good? So I believe the next one's the last slide. Again, this was just to introduce it, okay? I know it was very quick. There's a lot to process. But I just want to set it up so that we can begin to see how we can extend it to more complicated models. Next time will be simple linear regression. And I'm going to introduce a whole lot more probability blocks. Today, we were at the level of Minitab. Next week, we're going to be at the level of where I want us to be. And by the way, I don't know of any software that does it. Okay? So next week is the extension to simple linear regression. There will be fewer slides and more opportunity for conversation. Okay? So far, so good? Because I really want everybody who's really interested to understand the next lecture. Is that fair enough? Because the better you understand that, the better you understand the issues when I go to lecture 3, which is where the really cool stuff is occurring. And that's where I'm trying to exhibit what we should be doing as statisticians assigned in a collaborative project, working with engineers who don't necessarily appreciate what we do. Okay? I hope we have fun with that. Now, again, I apologize. I am dealing with everything from the original NASA data. If I can think of ways of giving you data that would be interesting to play with, I will. I've got this week to think about it, but I've been very focused on my NASA project. Yeah, yesterday, I spent all day after I came back from church to come up with final versions of appendices for our final report. And so I've been really kind of wrapped around this NASA project for a long time. There's a light at the end of the tunnel in English. We're going to come out of this soon. So I can't share anymore. I can't even tell you the carbon fiber composition. I talked about this one time in Israel about 4 or 5 years ago at Rafael, major defense supplier to Israel. Iron Dome, their production system for missiles from wherever, was done in Rafael in 3 to 5 years. So they were really interested, not so much in the statistics, but about the vessels. I could tell them nothing. I couldn't even tell them the material, because they would know what it is. I could tell the material, and you would just say, oh, I can't even tell you that. And I certainly can't show you parameters. Okay? So just want to let you know. However, the editor of Quality Engineering has agreed in principle to publish a 4-paper tutorial sequence where we summarize our whole story for this NASA project. At that point, it will have been released by NASA, and we will be able to show the parameter estimates, which will be really cool. But at this point, I can't share it. It hasn't been released. I don't want to get into trouble at this point. So, are we okay where we are at this point? Are we understand where I'm trying to go? What kind of questions do we have? I mean, y'all seeing, I see some nodding. I think some people are catching it. Some people here are being very polite, and that's good too. Are there any burning questions? Yonder.
You mentioned one type of experience with your brother life.
Yeah.
Have you done anything over there beyond your randomized design?
Not in this case, but hold the thought. Hold the thought. So, do we have a marker here?
Yes. Over there.
Oh, there we go.
Yes,
Andre, it's going to be almost like, it's not a split plot, but it's let me give you the crux of that. I'm skipping lecture 3. We're going to deal with stress rupture. We're going to, ultimately, our interest is putting dead weight on the fiber. So far, so good? But you got to apply the weight, okay? So this is a loading process. So we're going to have 3 stress ratios. And you're going to see this data next time. So this is time on test. We're going to have a lot of different times floating around when I get to lecture 3. There will be time on ramp. So this is the ramp. There's going to be time on hold. And time on ramp plus time on hold is time on test. So far, so good? Okay. This is a 2-parameter model. This is 3-parameter. The conjecture, this whole community's theory is that the failure mechanism on ramp is exactly the same failure mechanism as on hold. Therefore, they can combine the ramp and the hold data. Now, that's going to lead to a more complex experimental design. Are we making sense? So notice, in order to get to hold, it had to survive the ramp. So now I've got to be clever at how I specify the likelihood functions, which is going back to the structure of the data. So it's not going to be a split plot, but on the other hand, there are some similarities to it. Fair enough? Okay. And that's where I would love for us to be able to really understand what's going on. Okay? And that's why the editor of Quality Engineering is really interested in this, because it turns out it is physically impossible for this to be the same failure mechanism as that. It can't be true. However, that's what this community believes. No one had ever done an experiment where they could look at the ramp. It was like you had the weight already on the fiber, You kick the stand. So it was viewed as instantaneous load. And then they assumed there was some effective time, because there had to be some time at that load condition. This ramp is very similar to how you do a tensile strength test. That's exactly how we conducted the experiment. We could see at what times they fell. So far, so good. As a result, then, I can now model this in conjunction with this. And in a sense, then it's going to look very similar to a very different experimental design program. Fair enough? That's the problem of primary interest in lecture 3. Another example. This is called proof. Standard protocol in NASA, standard protocol with a lot of applications. When you get a vessel, before you put it on the spacecraft, you proof it, take it up to a higher load, and it's just a basic quality check. If it goes, poof, well, it's bad. And I found out before I stuck it in my spacecraft. So far, so good? Okay? But it's much higher than where you're really going to use it. So this would be used. This is proof. Okay? So a question is, one of the theories in this community is that by proofing it, you are creating damage that sooner or later you will see. Okay? Versus the possibility of you've eliminated all the weak and it'll last forever. The theoreticians who have never conducted a single experiment were assuming that it's going to hurt. The people who have real practical experience said, oh, it'll last forever. Guess what our experiment showed? It lasts forever. Yeah. So far, so good. But how I can convey this back to the engineers is going to go back to things like hazard plots. Okay? But now, this is where we're going to actually the cutting edge, because there's never been, the best that we can see in the literature, a proper analysis of this. There's nothing in the literature that gives a proper analysis. So the analysis we developed for this translates immediately over here. That's tenometric level. And then we're going to do what are called step tests. So in a step test, really, you're not, see on this test, when we allocated the test items, we said it's either going to be this load, or this load. So far, so good? So that requires a lot of test loads, a lot of test items, expensive. Well, it'd be cheaper if I could just run it up the ramp, okay? So this item, and then this level, this level, this level. So I started out with like 100 test items, and so many fail here, so many fail here. Interesting, nothing fails here, nothing fails here, some fail here, some fail here, and then we sense it. Okay? Question is, does it give us the same results as this? Reasonable question. This is Cadillac. This is pure. This is gold standard. This would be the real, what we would expect. This is a cheap way of trying to get that. Does that make sense? A lot of engineers swear that that's the way they should do it. Wayne Nelson has a really nice paper from 1980. Would set up a paper which leads to a major fallacy. And even he says he doesn't know if it's correct. We come up with the correct analysis. This does not give the same result as this. This shows that it will last much longer than if you do it this way. That means there are history effects. Just like there's a history effect here. Are you seeing how much fun I'm having? And if the engineer had his way, you would get exactly the opposite results. This is my contribution as the data analyst. It's taken us 2 years to get everybody persuaded except him. And by the way, a former editor of quality engineering is going to be a reviewer of this within NASA. Also one of my former PhD students, but that's not going to bias it. So I know the statistics will get a fair review. but we've dotted I's and crossed T's. I probably have written over 200 pages of appendices here with formal proofs. So this has been fun for me. So I'd like to share it to you. But that's also why we're trying to go through the series of how we can get to this point where we can talk about the really cool stuff. Fair enough? Okay. And even then, we can't send it to quality engineering until we get approval from NASA. And that hasn't been the team lead's focus. This is a cool team, by the way. It was formed as part of the NASA Engineering and Safety Center. It was formed after the Columbia accident. Team lead is at Jet Propulsion Lab. The subject matter composite reliability engineer expert is at Langley Research Center, which is in Hampton, Virginia. The database manager was a master's level chemist who went into quality. He was at Marshall Space Flight Center in Huntsville, Alabama. We have an aerospace engineer who's headquartered in Cleveland at Glenn. And then I've had my group at Virginia Tech. But we have met at JPL. That was pretty cool. They have a building, the main building at the Jet Propulsion Lab. They've got something that looks like light art. It's not. It's this little thing out there, and it's showing if the lights are going up, that's sending a message to one of the deep space spacecraft. If you see the lights coming down, it's receiving a transmission from the deep space spacecraft. Isn't that pretty cool? I got to see the most recent Mars rover when they were building it. I saw a Mars rover when it was hermetically sealed and testing at Langley. It's been really a lot of fun. But it's a very interdisciplinary team. And the tests were done in White Sands. Don't mean to bore you, but I thought it was cool. Any other questions, concerns? But Andre, I mean, actually I would like to do a follow-up experiment. I don't know the way to be able to do it, but in which case then we'll have to look at it's certainly going to be a subsampling problem. Because the engineer says, well, obviously this failure mechanism should be related to this failure mechanism. Maybe, maybe not, but this depends on material properties, and this depends on material properties. Does that make sense? Model this in terms of material properties, model this in terms of material properties. I'd love to do that experiment. But then we'd have to deal with different types of core that have very different material properties, and then repeat this experiment. But we have the equipment at White Sands to do it. So we don't have to reinvest in the equipment. Would that be cool? And then suddenly you're dealing with batches. So I would want different batches, but we're going to have multiple observations within a particular group. Now we're getting into more complicated experimental science. The procedure we did here was blocking because we were doing it over an extended period of time. I'll talk more about it when we get there. But it was a very good thing. It goes back to a paper of Soren talking about one of the side benefits if something goes wrong. Something went wrong. Very cool project. Any other questions? I think people want to go home. Thank you for your attention. I hope we have fun next week. I hope you understand my intent. I hope we have more conversation next time. I think this was fairly rudimentary, just get you started. But I hope you see where we're going. We're going to look at how we play with this next time. But this is the real interest, how to focus on this, and how do I incorporate the ramp into this and do it properly. Okay? I've made a lot of money off of this, and I've earned it all in the last 2 years just coming up with this stuff. Otherwise, I've just been ripping off the people of the United States of America. So, thank you very much.
Thank you.
Obrigada a todos. Só para lembrar que a próxima aula vai ser na segunda que vem. Depois a outra vai ser na outra semana, na terça-feira, dia 7 e 5.
público isso aí.
Oi?
Para o público,
Ah, tá.
finalmente.
Ah, sim, a gente está finalizando agora. Muito obrigada a todos que nos acompanharam pelo YouTube. Próxima semana nós continuamos com essa série de seminários. Muito obrigada.
It's going to be a new paradigm.